This is problem 635, Smith Van Ness, 8th edition. You've got steam at 2,700 kilopascals with a quality of 0.9. So that means the mass fraction of vapor is 90%. It undergoes a reversible adiabatic expansion in a non-flow process to 400 kilopascals. We then heat it at constant volume until it's a saturated vapor. We want to determine Q and W for this process. So we've got a two-step closed system process. We've got three states. So state 1, state 2 for step 1, and then state 2 to state 3 for step 2. The first step is, we're told, is a reversible adiabatic expansion. Whenever you see the two words reversible and adiabatic together, you should realize that means that delta S is equal to 0. Another way to say that is an isentropic expansion. So those are some of the phrases you'll hear in a thermodynamics class about that. So delta S is equal to 0 for that first step. The second step is we are heating at constant volume until we have saturated vapor. So if you notice in our in the first state, we have a mixture of liquid and vapor. 90% of it is vapor. We then do the first step, and then we do the second step until we have just saturated vapor. So let's look at the first step. We already mentioned it's reversible and adiabatic. If it's adiabatic, that means there's no heat transfer between our system and our surroundings. So this process is well insulated during that step. And so if we write our first law, that's just delta U is equal to Q plus W. Q is 0. And so delta U is just equal to W. And I've got 1, 2 for the state 1 to state 2. So what we need to do is we need to find delta U for this first step. Then we go to the second step. Second step is heating at constant volume. And what you should realize from here is that if you have constant volume, that means that there's no work done. Because remember, this is a closed process. Work is equal to minus P delta V, whether it's reversible or not. And so here we have delta V is equal to 0, so work is equal to 0. If we write our first law for our closed system here, you've got delta U for the second to third state is equal to Q, 2, 3. So this is nice. We want to calculate Q and W for the process, so that means that the only time we have work is in the first step, no heat. The only time we have heat is in the second step, where there's no work. So we don't have to worry about adding work and heat from different steps. We just calculate the work from one step and then calculate the heat from the second step, and then we're done. So start with state 1. And I've got a diagram here of what we know about state 1, state 2, and state 3. State 1, we know the pressure, we know the steam quality. We don't know the entropy. We don't know the enthalpy. State 2, we know the pressure. All right, it's a lower pressure. We're doing an expansion. We don't know the entropy, but we do know that it is equal to the entropy in state 1. And then state 3, we know that the volume of state 3 is equal to the volume of state 2, and that we are at 100% saturated vapor. So we know that we have a mixture of liquid and vapor here, and because of this statement, we've got a mixture of liquid and vapor there. So first thing that I would do in approaching this problem is fill in the state 1 conditions. We know we have a mixture of saturated liquid and vapor at 2,700 kilopascals. And so you can go to the steam tables and look up all the other information. Remember, what we really need to find for state 1 and state 2 is we need to find the internal energy at both of these states so that we can calculate the change in internal energy and the work. Now, this says that we have a saturated or a mixture of liquid and vapor at 2,700 kilopascals. So you've got two options for looking at the steam tables. The first option might be to say, okay, if I've got a saturated steam, I should use the saturated steam tables. And that's fine. There's nothing wrong with that. What you got to look at, though, is we don't know the temperature. All right, all we know is that it's at 2,700 kilopascals. So we're going to have to find out what the temperature is, and then we're going to have to find because we have a mixture of liquid and vapor, we're going to have to find the liquid value of U and the vapor value of U, and then use our extensive property information to calculate the total value of U at state 1. So if our pressure is at 2,700 kilopascals, we need to go to our steam tables, saturated steam tables, and you'll see, if you go to page 688, you'll see that you have if you turn your book sideways, the very last entry on page 688, we have a temperature of 228 degrees C and a pressure of 2696.5 kilopascals. And then the very next entry is a temperature of 230 degrees C and a pressure of 2797 kilopascals. And we've got internal energy for the liquid and the vapor at those conditions. But the thing is, if we want to calculate what the internal energy is, we're going to have to interpolate if we're going to use the saturated steam table. If we go to the superheated steam table, and we look up 2,700 kilopascals, we see we have, if you go to, so that will be on page 708, we've got an entry for exactly 2,700 kilopascals. So page 708, look in the very left column, 2,700 is our pressure in kilopascals. Our temperature, which is below it, in parentheses, is 228.07 degrees C. And then if we look at the very next two columns, the next column are the properties of saturated liquid, and then saturated vapor is our next column after that. So what we can do then, we don't have to do any interpolation by using the superheated steam tables, which that's a win in my book. All right. And so we just read off the internal energy for the saturated liquid, which is 977.968. And then we read off the internal energy for the vapor. And so I've got U1L and U1V, which is 2601.8 kilojoules per kilogram. Since we have a mixture, we then calculate the total internal energy at state 1 using our extensive property relation. And so we know that it's 90% vapor, and this is a mass basis, and so we're able to calculate, and you can see it's a weighted average. This is just a weighted average formula of the internal energy. So our internal energy here is 2439 kilojoules per kilogram. So we've got that part. So now we have U1. We want to find what U2 is. The problem is we don't know what the temperature is. We know the pressure. We know the pressure is 400 kilopascals. But if we go to steam tables, you see that that really doesn't tell us much because there's lots of entries for 400 kilopascals for all sorts of temperatures. So what do? Well, now is when we use the information that we know that this step is reversible and adiabatic, which means that delta S is equal to 0 for this step. So we know if we know what S1 is, the state of entropy at state 1, we set it equal to S2, then we can use S2 and P2 to figure out what U2 is. So hopefully that makes sense. So the first thing we're going to do is we're going to calculate the entropy at state 1. So that's what I've got here. So we go back to our 2700 kilopascals. And we have our saturated liquid, which is 2.5924. We have our saturated vapor, which is 6.2244 kilojoules per kilogram Kelvin. Put that into our extensive property relation. This is our entropy. We then set that equal to S2. So now S2 is the same. Now we have enough information to figure out where we're at with state 2, because now we know the entropy and now we know the pressure. So what do? We go to our, again, I would use, since this is a nice round number, I would still use a superheated steam table. I would go to 400 kilopascals. That's going to be on page 696. So page 696, 400 kilopascals. And we need an entropy of 5.861. And so if I look at that, if I look at the entropy for saturated liquid, that's 1.7764. If I look at the entropy of a saturated vapor, that's 6.89. So let me pull this over here. All right. So 5.86 is in between those values. 5.86 is in between the value for the saturated liquid and the saturated vapor. So let me just pull those over here. So again, here's our temperature. Our temperature, we don't really need this, but I'm putting in here, it's 143.62. Saturated liquid, 1.7764. Saturated vapor, 6.8943. All right. And as you'll see, as you superheat, as you would expect, going to higher and higher temperature, your entropy just keeps just getting bigger and bigger. So what this is saying, because our entropy value is in between these two levels, that means we have a mixture of vapor and liquid in equilibrium. So what we can do then is we can solve, what we need to do is we need to solve for the mass fraction of the vapor and the liquid. We know the total entropy of our system. We know the individual components of our liquid entropy and our vapor entropy. Now we just solve for X, the steam quality, at state 2. And we do that, just rearrange the equation that we had up there, and we get a steam quality of 0.798, so about 80%. So we've gone from 90% vapor to about 80% vapor. Now we have enough information to where we can calculate the internal energy at state 2. Because now we know the pressure, we know the temperature, of course, and we know how much of our material is at is going to be liquid and vapor. So I forgot to bring that over there. So we look up the at 400 kilopascals, internal energy of the liquid, 604. Internal energy of the saturated vapor, 2552.7. Plug that into our extensive property equation, and we get U2 is 2159 kilojoules per kilogram. And so once we know that, we can calculate work. Work is delta U. Make sure we get our signs right. So it's U2 minus U1. That's going to be minus 280 kilojoules per kilogram. Does that make sense? Should this be negative? We get our sign right? Well, this is an expansion, right? This is an expansion, so our system's doing work on the surroundings. Our internal energy is getting lower. That is done that comes from the work. All right, so now the second step. So we've got the work, we're done with work. There's no work in the second step, remember. So now we need to find Q. So our second step is constant volume heating until we get saturated vapor. So right now, remember, we're at about almost 80% vapor. We're going to heat this up until it's 100% vapor. And again, since it's constant volume, there's no work done, and so our first law reduces to this point. To this equation. Q is equal to delta U. So here I've just written down some information. I know P2, I know T2, I know U2. I just calculated that. We need to find V2. So why do we need to find V2? The reason is because V2 is going to equal to V3, and that's going to give us information about how to solve this problem. So what I've got here, I've got V2 of the liquid, so we're at state 2 now. All right, saturated liquid volume 1.08, saturated vapor volume 462. I'm going to, using my steam quality, I'm going to calculate my total volume, total molar volume of this system, my overall volume. And so that's going to be my overall volume. So V2 is going to be 369. It's going to be an average, weighted average, 369.135 centimeters cubed per gram. I'm going to set that equal to V3. So I'm going from V2 to V3 where the volume stays constant. The other thing that I know about state 3, if you look up when we tabulated everything, we don't know anything else. We don't know T, we don't know P, but we do know that it's 100% saturated vapor. And so what we need to do then is we need to find where will we find a saturated vapor volume of 369.135. And so this will be where if you were to use you could use either the steam tables, or sorry, the saturated steam tables or the superheated steam tables. Our volume, our saturated volume is going to be 369. And so if I look at, I'm going to use the superheated steam tables. So what I'm going to do is I'm just going to look in the saturated vapor column. I'm going to see if I can find where we get a molar volume of about 369. And so I'm starting on page 696. At the top at 325 kilopascals, it's 561. It starts going down, so I move down further. And then you can see at 500 kilopascals, I'm at 374.68. And then at 525 kilopascals, I'm at 357.84. I'm at 357.84. And so what that is telling me that my steam is going to be in between those two pressures, all right? And if I want the temperature, it's going to be between those two temperatures. So in the first version of this video, I interpolated with pressure, but I called it temperature. And so what I'm doing is re-recording this with making sure I get it straight, where I'm going to be interpolating now between 151.84 degrees C and 153.69 degrees C. I'm going to interpolate to find the temperature that I'm going to be at, and then I'm going to use that information to calculate the internal energy and then eventually calculate Q. So at a temperature of 151.84, my molar volume is 374. At a temperature of 153, my molar volume is make sure I'm reading this right, is 357. All right, and so and this is for, this again is for the saturated vapor. So I interpolate. My actual molar volume is going to be 369.135. So X is my independent variable. M is my dependent variable. That's going to be temperature. And I solve, and the temperature is going to be 152.449 degrees C, or if I put into Kelvin, about 425.6 degrees Kelvin. So what that does, this tells me, now I could have interpolated for pressure like it did before, only I called it temperature, or I could interpolate for temperature here. But what that gives me is that gives me enough information to where I can now calculate the internal energy of state 3. And so now my independent variable in my interpolation is going to be temperature. So I'm going to be going between 151.84, 153.69. The actual temperature that I want my internal energy at is 152.449. And then if you read off the internal energies, at 151.84, the internal energy is 2560. At 153.69, the internal energy is 2561.8. We interpolate to find the internal energy at state 3, which is at 152.449, and we get a value of 2561 kilojoules per kilogram. So now we have the internal energy at state 3. We have the internal energy from state 2 that was calculated above, and we can calculate the heat transfer between state 2 and state 3. So Q is equal to delta U. So that's equal to 401.3 kilojoules per kilogram. So as you saw, even the best of us make mistakes, and especially with interpolation, the only thing I can tell you is try not to do what I did and get mixed up. It didn't really hurt my solution, but it certainly was something that was not correct. Try to keep straight what you're doing when you're interpolating. The other thing is just realize that a lot of what this problem was doing was just testing you on being able to use the steam tables. If this had been an ideal gas, this would have been, this would have been such an easy calculation. Right? If this were an ideal gas, we would have done this in chapter 3, where delta U is equal to W. Delta U for an ideal gas is just CV delta T. And so work would have been equal to CV delta T. But what we got to realize is there's no way that this is an ideal gas. In fact, we've got a mixture of gas and liquid. And so we're going to have to use the property tables. So that is what this problem is really testing you on, is if you can use the property tables and then some extra information thrown in with the second law, where you say we now have a reversible adiabatic expansion. So when they write this problem, they say it's reversible and adiabatic. If we had done this in chapter 3, I would have probably given you I would have given you the pressure, and then I would have had to have given you the temperature or the volume, so that you could for a complete gas mixture, or a complete pure ideal gas, so that you could have done the problem. And then again, they are using the fact that now we know something about how to handle two-phase mixtures and things like that in specifying the conditions at state 3. And so, you know, overall, what I want you to be able to do is overall to see that this is still a somewhat simple problem, but now with having two phases present, having to look things up in the steam tables, having to use a little bit of second law information and calculate these extensive properties when you've got mixtures of liquids and vapors, that's where they're throwing you the extra material. And that's where all these additional calculations take place. If I had given this as a quiz question from chapter 3, it would have taken you, maybe about 10 minutes, 5 minutes to do this calculation. With all these other complications to it, and they're just decorations. They're just making this problem look fancy and hard, but at the core of the problem is still just work is equal to delta U, heat is equal to delta U for these two different steps. And so we're able to solve the problem through this. So the main thing I guess I can say is try to keep track of what you're doing. If you need to, jot an outline down on another screen or on a piece of paper that you're working from. And also make sure you're careful in reading the steam tables. Don't do what I did the first time and misreading the pressure and temperature, getting those mixed up. If you avoid those problems, you should do well.